Relative reactivities of carboxylic acid derivatives. The relative reactivities of the carboxylic acid derivatives is going to depend on the basicity of the substituents that is attached to the acyl group. Let's say that these are all your acyl groups. So, and here are the groups that are attached to the acyl groups, and the reactivity of the carboxylic acid derivatives is going to depend on these groups, Cl minus, OR minus, OH minus, and NH2 minus. And we know that the Cl minus is the weakest base of all of these. So this is going to be the weak base, and whereas the NH2 minus is a strong base. And therefore we can expect the acyl chloride to be more reactive, whereas the amide to be least reactive. So this is going to be the most reactive, and this one to be the one that's least reactive. The first step in the nucleophilic addition elimination reaction is the formation of tetrahedral intermediate. But it is said that the weak bases are going to favor the formation of tetrahedral intermediate faster. Now why? What is the reason behind this? Now let's take a look into the basicity of Y. Let's say that Y is a strong base. If Y is going to be a strong base, then these electrons will be donated on here to form the double bond, and the electrons in the carbon-oxygen double bond is going to be kicked onto the oxygen to give this resonance contributor. But there is a problem with this resonance contributor. This carbon is not very electron deficient. So if this is not electron deficient, then you cannot have a nucleophile going and attacking this carbon. But in the case of weak base, since they are not ready to share its electrons, this is going to be this resonance contributor, which has a positive charge, is going to be a less contributor. And therefore, the nucleophile can go and easily go and attack this carbon to form the tetrahedral intermediate much faster. Also, the weak bases make the collapse of the tetrahedral intermediate much faster, because we know that the weak bases are easier to eliminate from the tetrahedral intermediate. Now that we have understood how the basicities of the different groups is going to affect the relative reactivities of the carboxylic acid derivatives, we can see how one carboxylic acid derivative can be converted into another. So here is the relative reactivities of the different carboxylic acid derivatives. So from here you can definitely see that the acid chlorides are more reactive than esters and the carboxylic acids and amide. We have to keep in mind that you can convert a more reactive carboxylic acid derivative into a less reactive one. So an acid chloride can be converted to any of these, but an amide cannot be converted into an acid chloride or ester or carboxylic acid under normal conditions. So here is an example. So this is an acid chloride. When you react it with the methoxide ion, which is a nucleophile, obviously since this is going to be the stronger base, it's going to displace this weaker base, right? So this is a weaker base, and the stronger base is going to take the place of the weaker base, and it's going to give us the ester. But the opposite reaction, which is the conversion of an ester into an acid chloride, is not possible, since here you have a strong base, and this one is comparatively a weaker base. A weaker base is not going to go and displace the stronger base. Or in other words, even if the Cl minus is going to go and attack this carbon to form the tetrahedral intermediate, in the second step, the OCH3 minus will not be displaced off to give the product. So there will be no reaction. Here are the reaction coordinate diagrams for the three different conditions that we have talked about. In the first case, we have a weaker nucleophile, weaker incoming nucleophile. Here we have a stronger nucleophile. And here, both the leaving groups and as well as the incoming nucleophile, they're going to have the same basicity. So in the first case, since you have a very weak nucleophile, the base that is already present in the molecule is not ready to leave, and therefore it has to climb a very high energy barrier in order for the reaction to give us a product. So this is not going to happen. But if you have a strong nucleophile, the base that is already present in the molecule is ready to leave, and therefore you can see that the product can be formed easily. But when the leaving group and the nucleophile are going to both have about the same basicity, then the reaction can go hop in both of these directions. right, to give us the product, both the product and as well as the reactant. The mechanism for the nucleophilic addition elimination reaction for the conversion of one carboxylic acid derivative into another is pretty much the same. But you have to pay attention to what kind of nucleophile you're using. So if you're going to use a negatively charged nucleophile, then there are only two steps involved in it. The first step is the formation of the tetrahedral intermediate, and the second step is the collapse of the intermediate. But when you use a neutral nucleophile, there is one step in the middle, which is basically the deprotonation of the protonated tetrahedral intermediate. Let's now take a look into the mechanism for these two different situations. Let's say we have the methoxide ion, which is a negatively charged nucleophile. So in the first step, this nucleophile is going to make a nucleophilic attack on this electrophilic carbon, thrust these electrons onto oxygen. Let's write down the structure of the tetrahedral intermediate that will be obtained. So this is the structure of the tetrahedral intermediate, and in the next step, these electrons are going to come back in here, and because now Y is the best leaving group, it is going to leave. Okay, and it's going to provide us the final product, which is an ester. So there are only two steps. But when you have a neutral nucleophile, there is one more step, which is the deprotonation of the tetrahedral intermediate. Let's see what's happening here. Here we are going to take methanol. Okay, as you can see here, this is a neutral nucleophile, and the lone pair of electrons present on oxygen is going to make a nucleophilic attack on this electrophilic carbon, thrust these electrons onto oxygen. Okay, so that is going to give us a tetrahedral intermediate, but this time the tetrahedral intermediate is going to be protonated, right? Because this oxygen, which is trying to form a bond with this carbon, is going to have 3 bonds. So this oxygen is going to have a positive charge because it's lost its lone pair of electron to form this bond, right? And in the next step, the base is going to come and abstract this hydrogen and neutralize this positive charge on oxygen. So that would be this new step that is added here. So now this is the regular tetrahedral intermediate, which is going to thrust these electrons onto to form the double bond between carbon and oxygen. And again, since Y is a good leaving group here, it's going to leave and give us the ester.